Welcome to lesson 9, where we will be describing large and small numbers. And we're going to do that by finding out how to use powers of 10 to write those large and small numbers. To be successful, you'll be given a large or a small number. You'll be able to write an expression equal to it using a power of 10. In this warm-up that we start with, you're given 3 different tables: one expression table, a values table, and a word table. Your goal is to match the expression to the value and the value to the word. Pause here and take a moment to try this on your own before moving on. Now that you've had some time to match them, let's go through them together. 10 to the negative third would match with this value here, which we would say is milli. So 1 over 1,000 would be milli. 10 to the sixth matches with this value here, which would be million. 10 to the ninth matches with this value here, which would be billion. 10 to the negative second matches with 1 over 100, which is centi. 10 to the 12th matches with that top value, which is trillion. And 10 to the third matches with 1,000, which is thousands. So if you wanted to put this into perspective a little bit and think about some real world situations, you could think of 10 to the third, the thousands, maybe representing the population of a school, where 10 to the sixth, being a million, could represent the population of a state. 10 to the ninth maybe would represent a specific country. 10 to the 12th, a very large number. We're talking about trillions there, so that might represent stars in a galaxy. And then keep in mind that those negative exponents represent much smaller numbers. And so we'll be working with both types in this lesson and rewriting them with the powers of 10. We start with a base 10 representation. And before you start working on your own, we're just going to go through some examples where we're going to look at this small square down here and give it a different type of representation each time. So let's start by thinking that this small square represents a tree. And our goal is to think about the big picture of this whole entire diagram. So if one small square is a tree, we know that this rectangle would be 10 trees. The second rectangle is 10 trees, and the entire big square would be 100 trees, totaling 121 trees. But what if we change that small square and we say that the small square now represents 10 books? So that's going to change the entire value of the diagram. So we move to the rectangle. The rectangle would have to be 100 books because each small square is 10. So again, there's 10 of them. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's where you're getting 100 books. That second rectangle would be the same thing. And then moving to the big rectangle, there are 100 of those squares and each square is 10 books. So there's 1,000 books there. Altogether, we would say there's 1,210 books total. Let's change this again. Let's say that the small square this time represents 1 million stars. So if the small square is 1 million stars, we know again that rectangle, there's 10 of those small squares. That would have to be 1 million times the 10 squares that make up that rectangle. So that's 10 million stars. Same thing for that second rectangle. Moving to the last representation, we now know that this is 1 million times 100 small squares. So we would say that there's 100 million here. Altogether, this entire representation would represent 121 million stars. Let's change it again, but let's look at something a little bit smaller. Let's think about time. Let's say that this small square represented 1/10 of a second. Well, that means that that rectangle, each of those small squares, a tenth, 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, 10/10, right? So that's going to be 1 whole second. Same thing with that second rectangle, which means that our big square representation would have to be 10 seconds total because there's 100 small squares. Altogether, that would represent 12.1 seconds. In this last one, we're going to think of something with a power of 10. So we have 10 to the third is going to represent the small square. So again, 10 small squares represent 1 rectangle. So we would have to multiply that by 10, which gives us 10,000. Same thing for the second rectangle. The third figure here, the big square, would now be 10 to the third times 100 of the small squares, which means we'll have 100,000. Altogether, this would represent 121,000 people total, because we were talking about 10 to the third people being the representation of the small square. Now that you kind of understand how to navigate this representation, pause here and you're going to work through the activity on your own, where you are going to be matching the representations that are listed at the bottom, A, B, and C, to the expressions that you are given. Now, you might find that some of those expressions can be represented with maybe multiple diagrams, and you may reuse a diagram more than once. Pause here and give that a try. Okay, you've had some time to work. We're going to start off by going through the first expression, which is 2 times 10 to the negative first plus 4 times 10 to the negative second. So you might have matched this with C, and here's why. If we think about one of those small squares being 10 to the negative second, we see that there's 4 of them, right? So that's that right side, that plus 4 times 10 to the negative second. But then again, think about how we applied the relationship in the intro before you started the activity. So there's 10 of those times 10 to the negative second. If you think about what this means, this really means you have 10 to the negative first, right? Think about some of the rules we've talked about. Think about the way we've written factors out, so you could kind of understand how that is coming together. Now, C was not the only choice you could have matched it to. Oh, there's the 2 there. Let's see. You could have also matched it to B, and here's why. If we think about one big rectangle representing 10 to the negative second, well, think about what that means for one big square. That would mean that that has to be 10 to the negative first. In a similar fashion, you have 10 rectangles in that big square. So 10 to the negative second times 10 is giving you that 10 to the negative first. And so you see, all combined, you have 2 of those squares plus the 4 rectangles, and that's where that's being matched. In part B, this one you should have matched to A. If a small square is 10 to the negative third, you again have 4 of those, so that's where you're getting 4 times 10 to the negative third. And now you have to think about, you have how many of those small squares in one big rectangle? You have 100 of them. So you're really thinking of this as 10 times 10 times 10 to the negative third, or you can think of it as 100 times 10 to the negative third. But overall, that's 10 to the negative first. Think about your factors. You have 2 factors of 10 times 1/10 times 1/10 times 1/10, right? So that leaves you with 1 over 10, which is equivalent to 10 to the negative first. Moving into part C, you could have also matched with A, and here's why. If the small square is 10 to the negative, or I'm sorry, 10 to the positive first, again, there's 4 of those, so that's where you're getting the 4 times 10 to the first. That's not supposed to say a negative, so ignore that negative. Then here we have 10 times 10, or you could have said 100 times 10 to the first, which is equivalent to 10 to the third, and there's 2 of those, so that's where the 2 times 10 to the third is coming from. And in part D, we could have matched this to B. We could have said one rectangle is 10 squared, and there's 4 of those. And so one big square would have to be equal to 10 times 10 squared, right? Because there's 10 rectangles in the big square, which is 10 to the third, and there's 2 of those. Now you could have also matched this to C as well. So you could have thought of the small square is 10 squared. There's 4 of those. And then you know you have to multiply 10 squared by 10, and that would be 10 to the third. So again, could have looked at that 2 different ways. There's those 2 there. In that last piece, you had to write an expression to describe the base 10 diagram if each small square represents 10 to the negative fourth, and then think about the entire value of this expression. So let's start with the small square. We know that that's 10 to the negative fourth. We have 4 of those, so we think of it as 4 times 10 to the negative fourth. Let's move to a rectangle. We know that one rectangle includes 10 small squares, so we have 10 times the value of a small square, which is 10 to the negative fourth. That gives us 10 to the third. So we now know that we have 5 rectangles that are each worth 10 to the negative third. Our big square has 10 rectangles in it. So we are going to do 10 times 10 to the negative third, which is equal to 10 to the negative second. So there's 2 of those, So 2 times 10 to the negative second. So there's your first expression, but we're going to evaluate it and find out what is the value of this entire expression. Now, think about what's happening. We started with that small square. Every time we try to determine the value of each of those representations, we're multiplying by 10. If you remember in some of the previous videos, every time you multiply by 10, your exponent is getting bigger. When you multiply by a tenth, your exponent would be getting smaller. So start thinking about those connections as we're moving through these components. If we evaluate this, this would be 2 over 100, right? Because 10 to the negative second is a tenth times a tenth, and there's 2 of those. Here we would have 5 over 1,000 and 4 over 10,000. Overall, that value is represented by the decimal 0.0254. So how does changing the value of the small square change the value of the expression? Changing the value of the small square changes the powers of 10. The long rectangle always has an exponent that is 1 higher than the small square, and the large square always has an exponent that is 2 higher than the small square, right? So you're going from times 10 to the rectangle, and then if you're starting at that square, you're really doing times 100 to get to the big square. So that's why it's 2 higher than the small one. Base 10 diagrams help us make sense or explain the exponents in powers of 10. When using diagrams, grouping 10 of the next smaller unit means multiplying by 10. When dealing with powers of 10, multiplying by 10 increases the exponent by 1, which we just discussed. Likewise, decomposing a base 10 unit into 10 of the next smaller units means multiplying by a tenth, so the exponent in the power of 10 goes down by 1. So again, making those connections from some of our previous videos. Using powers of 10 makes it easier to communicate about very large or very small numbers. We can write in a smaller space. It's also faster to read, and it's easier to understand the size of a number and to compare numbers. It also helps us avoid errors of missing zeros or extra zeros. How can we describe a large number like 123 billion? So think about it like this. Here's what 123 billion looks like written out. We could think of that as 123 times 1 billion. But we could write it smaller by writing 123 times 10 to the 9th. Same value, but it takes up less space. We could also write it as 12.3 times 10 to the 10th, or even 1.23 times 10 to the 11th. Think about a decimal like this. How can we describe a small number with so many place values here as a decimal? So we can think of this as 789 times 1 over 10 billion, or 789 times 10 to the negative 10th, 78.9 times 10 to the negative 9th. These are all equivalent ways that we can write this number. They all mean the same thing, but again, writing it with that base 10 allows us to write it in smaller space. You can read through that lesson summary if you choose to. Otherwise, you were successful at this lesson if you can write an expression equal to it using a power of 10 when you are given a very large or a small number.